Welcome back. We're now going to deal with vector addition and subtraction. Remember, vectors have magnitude, direction, and units. All right, so first, vector addition. A way to think about vector addition is two vectors that are carried out one after another. So you go from point A to point B, then point B to point C. All right, so think of this as two vectors carried out in succession. All right, so for example, if you have a vector A and you have a vector B, B, not A again, B, A plus B would mean you would follow A and then you would follow B. All right, so let me write that a little bit more carefully. So let me put a point 1 and a point 2, and then B would start at point 2 and go to point 3. So how would that look? All right, so we actually connect these. So that it's B is actually starting from the endpoint of A. So let me rewrite A. Here's A right here. All right, and then B starts where A ends. Here's B. Okay, so you're going from 1 to 2 and 2 to 3. There. All right, so, but you don't have to. What you can do is you can go, if you're doing A plus B, you can go right from 1 to 3. And that's what A plus B is. That's going to get you to the same place. This is called the resultant. All right, the resultant, the result of going along A and then going along B is the same as the result of going along vector R. They get you to the same place. All right, so R represents the three lines meaning like a definition, resultant. Okay, now, just like in regular addition, the order of addition does not matter. Not matter. Now, I didn't draw these to scale, and I strongly suggest, if this doesn't make sense to you, or even if it does, it's a good exercise, I've done it a bunch of times, to actually take graph paper, take a protractor, make one of these, horizontal or vertical, just to make your life easier, but make the other one at an angle, and draw A plus B, and then draw B plus A, and you'll find that the resultant you get will be the same. Okay, you get the same vector. It'll be the same length, same direction. All right, but don't take my word for it. Prove it to yourself. All right, now, one thing to understand is that the magnitude of r, all right, will always be less than or equal to the sum of the magnitudes of A and B. Okay, and you can see that if you think about that for a minute. If I take A, so here's the biggest R can be, right? Well, not here, obviously, but, all right, so here's them now. Now, if I take this angle and I open it up so that now I'm like this, well, then R is getting bigger, right? It's getting bigger and bigger and bigger as I make this angle closer to 180. When this angle is 180, what's happened is here's B and here's A. Right? So the magnitude, and that's the same as R, right? Same thing. A plus B is R. So the magnitude of R in this case is the sum of the magnitude of A and B exactly. And it's as big as it can get, because if you increase the angle more, well, now you've just gone and, made B bend the other way, and now the resultant is smaller again. All right, so the magnitude of R is always going to be less than, and at best equal to, the magnitudes of A plus the magnitude of B. Stop it. All righty. So, we're going to write a couple of mathematical laws that'll be very familiar to you. This all, I assume, is, you've seen all this before, but we're going to be using it a lot, so it's good to go over it. If you don't get stuff, please talk to me, figure it out, because we're going to be using this. Okay, so the commutative law. Just like for arithmetic, A plus B equals B plus A. And this, I spelled addition wrong. Let's do that right. Addition, come on. Addition. There we go. All right, that's the commutative law. The order, when you're doing addition, the order of adding doesn't matter. And I just put 2 vectors there, but this will work for 3, 4, as many vectors as you want. As long as you're adding them, it doesn't matter. The order does not matter. All right, and again, prove it to yourself. Make up some vectors and do them out on graph paper. Prove it to yourself. Okay. Also, we have the associative property. The associative law, that one is if you take A plus the quantity B plus C, that's the same as the quantity A plus B plus the vector C. Again, it's just saying that the order does not matter. Now, that's for addition. Subtraction, as you know, is a different story. But just like in mathematics, we can add a negative number and still use the laws of addition. We can do the same with vectors. So the negative of a vector, let's just write this so this is clear. The negative of a vector has the same magnitude opposite direction. Okay? So mathematically, they would say this, that A plus the quantity minus A equals 0. So if this is A, then this is minus A. All right, exactly the same magnitude, opposite direction. So subtracting vectors, the way to think about subtracting vectors, I'm not working good with the spelling here. Subtracting vectors. What you're going to do is just turn them into addition problems. Okay, subtracting vectors, let's write it this way, can be thought of as adding the negative of the second vector. All right, so to subtract two vectors, A and B, okay, it would be like this. So we want these subtracted. So we change that to A plus minus B. Okay, so if we go back to our vectors that we started in the first place, A, B, and minus B. Okay, so that means that A minus B, okay, just rewriting that over there, A plus minus B, so that would be this, like this, A, then plus a minus B, minus B. So the resultant is going to go from the beginning of A to the end of B. All right. Once you get to this point, it's just addition of vectors. That's all it is. Same as before. All right. So now we did addition, subtraction, multiplying. And we're going to take the case of multiplying by a scalar. This is an easy one. Multiplying a vector by a scalar multiplies the magnitude. Of the vector. Okay, multiplies the magnitude of the vector. It doesn't multiply the direction. Okay? So, for example, 3a has 3 times the magnitude of vector A. But, oh, and is in the same direction. Okay, so if A, let's make A 1, 2, 3, 4 of these little squares right here. If that's A, then 3A is going to be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. That's 3A. All right. Similarly, minus 3A is in the opposite direction of A. With 3 times the magnitude of A. So, if this is A, let me do it over here. So, if this is A, 2, 3, 4, then minus 3A, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, minus 3A. The minus in the opposite direction, 3A, 3 times the magnitude of A. Okay, so I'm going to end up here by presenting you with a problem. So you've got 2 vectors. You've got a vector B here, and you've got a vector A. Okay, and you've got, ooh, that was weird. Okay, let's try that again. Vector here, a resultant. That is at some angle theta. Theta. Okay, so here's what you do. Here's the situation. You start at point 1. Okay, here's 1. Walk 3 miles due east, which is vector A. Then turn and walk 4 miles due north, which is vector B. What is the magnitude and direction of that resultant, the angle from the horizontal? Okay, I'm going to leave you with that to think about, and I'm going to pick that up on our next video. All right, so we'll see you soon.